Today we'll cover section 11.2. This is the introduction on infinite series. And remember that test 3 is next Friday. It will be over sections 10.1, 10.2, 10.3, 10.4, 11.1, and 11.2. And later today I will email the test 3 review sheet. Okay, so chapter 11, section 2. So we begin with an infinite sequence. Let A sub n be an infinite sequence. So remember what that means. It's just a list of numbers, A sub 1, A sub 2, A sub 3, and so on. The infinite series, or just the series of an infinite sequence, A sub n, is the sum of all of the terms from that sequence, A sub n. And one way to denote that is using sigma notation. So sigma notation, as you know, is used for sums when you're adding a bunch of terms. So the infinite series, A sub 1 plus A sub 2 plus A sub 3 plus dot, 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 can be denoted this way. The sum of the A sub n terms from n equals 1 to infinity. Some infinite series converge to a finite number, whereas other infinite series diverge. So as you know by now, there's different ways that divergence can occur. That will come up today. So our first example of a series, the sum of n squared as n ranges from 1 to infinity. So we're just adding the squares of the natural numbers, 1 squared plus 2 squared plus 3 squared and so on. And it's not too difficult to believe that this diverges to infinity because we're continuing to add even larger and larger numbers forever. So we get divergence to infinity. This next example of an infinite series, the terms are -1 to the n plus 1. So when we add those, we have +1, -1, +1, -1, +1. So each of the partial sums oscillates between 1 and 0. So it doesn't get close to any number, it just oscillates between 1 and 0, so we say that it diverges. Okay, here's our third example of a series. The sum of terms 1 over 3 to the n as n ranges from 1 to infinity. So that's just 1 over 3 to the first plus 1 over 3 to the second plus 1 over 3 to the third, and so on. This infinite series converges to the number 1/2. So even though we're adding infinitely many terms, well, if you could ever get to infinity, it would be equal to 1/2. So we just say that this infinite series of terms 1 over 3 to the n as n ranges from 1 to infinity equals 1/2. We will learn some things about how to show whether an infinite series is convergent or divergent. Sometimes we will be able to find what a convergent series converges to by looking at the corresponding sequence of partial sums. If you've never encountered a sequence of partial sums, it's not that hard to understand, but make sure that you do understand it. So given a series of from a sequence a sub n, this means we're adding the terms from the sequence. So it's a sub 1 plus a sub 2 plus a sub 3 and so on. We denote by S sub n its nth partial sum. Okay, so I have a typographical error here. In this, to the right of the sigma, it should be a sub I instead of a sub n. So S sub n is the sum of the first n terms from the sequence a sub n. So to reiterate, this sequence of this partial sum is just a sub 1 plus a sub 2 and so on up to a sub n. So S sub n forms a new sequence. It's called the sequence of partial sums. Okay, just to reiterate, S sub 1 is just the first term from the sequence a sub n. S sub 2 is the sum of the first two terms from the sequence a sub n. So S sub 2 is a sub 1 plus a sub 2, and so on. So S sub n is the sum of the first n terms from the sequence a sub n. So make sure that you know that the sequence of partial sums is what S sub n is. If the sequence of partial sums, the sequence of the S sub n terms, is convergent, then we can say that the limit of S sub n as n approaches infinity is equal to S, a finite number. S is what it converges to. Then the infinite series is convergent, and its sum is S. So that is, if we add all of the terms from the sequence a sub n from n equals 1 to infinity, and it converges to S, then we can just say that the infinite series is equal to S. So note that the limit of the sequence of partial sums is equal to S. Therefore, the infinite series converges to S. Okay, if the sequence of partial sums S sub n is divergent, then the series of the a sub n terms is also divergent. Okay, then some other notation. This is just to reiterate what we've discussed. The infinite series of the a sub n terms, as n ranges from 1 to infinity, that's equal to the limit of the sequence of partial sums, S sub n, as n goes to infinity. And we can also represent the S sub n as the sum of the first n terms from the sequence a sub n. Okay, let's move on to the next page. The sequence a sub n, as n goes from 1 to infinity, is called a geometric sequence if a sub n is equal to a times r to the exponent n minus 1, where the number a does not equal 0. Each term in a geometric sequence is the product of the previous term and the common ratio. So we can find the common ratio in a geometric sequence if we divide a sub n plus 1 by a sub n, or this just represents any pair of consecutive terms from the sequence a sub n. Divide a sub n plus 1 by a sub n. So a sub n plus 1 is a to the rn, and we're dividing by a sub n, which is a times r to the n minus 1. And this simplifies to r. So this number r is referred to as the common ratio. And the corresponding geometric series is denoted this way. It's the sum of the terms a times r to the n minus 1 as n ranges from 1 to infinity. Okay, the sequence of partial sums for a geometric series. So S sub n is the sum of the first n terms. So this is like a times r to the 0 plus a times r to the first, and so on. So you can see that there are n terms there. Or you can denote this S sub n as a sum of a times r to the I minus 1 as I ranges from 1 to n. This is the S sub n is the sequence of partial sums. Hey, it's pretty easy to tell that when r is equal to 1, the geometric sequence diverges. If r is 1, then we're just S sub 1 is a, and S sub 2 is a plus a, or 2a, and so on. S sub n is n times a, so the limit as n approaches infinity of n times a is either positive or negative infinity, depending on whether a is positive or negative. Okay, so let's go to work. Let's find a formula for S sub n. That's the sum of the first n terms from a geometric sequence. We're assuming that r does not equal 1, since we already know that when r is 1, the geometric sequence diverges. Okay, any ideas on how to start by finding a formula for S sub n other than just the sigma notation? Is that a yes? No? Hey, no ideas? Okay, what I'll do is I'll write out what S sub n is. So starting at I equals 1, we have a times r to the 1 minus 1, or a times r to the 0, it's just a. Then we add the next term, it's a times r to the first, and then plus a times r to the second. and so on. At the other end, let's write three terms, a times r to the n minus 3 plus a times r to the n minus 2. And then the nth term is a times r to the n minus 1. Okay, are we all in agreement about that? And the next line, I'll write down an equation. The equation I get if I multiply both sides of this by the common ratio r. So I'll multiply the left-hand side by r times s sub n. Multiply each of those terms by r, I get a times r plus a times r to the second plus a times r to the third, and so on. When I multiply the last three terms by r, I get a times r to the n minus 2 plus a times r to the n minus 1 plus a times r to the n. Hey, what should I do next? Looks like it's getting more complicated before it's getting easier. That's often the case. So let's subtract the bottom equation from the top equation. So in other words, on the left-hand side, s sub n minus r times s sub n. And what happens on the right-hand side? We're subtracting the terms from the bottom equation, or from the bottom right side. We're subtracting them from the terms above. Notice we get a bunch of cancellations. A times r to the first, this is a times r to the first. When we subtract, those cancel. Then the next pair of terms cancels when we subtract. A times r to the second minus a times r to the second is 0. And they continue to cancel out. So at the other end, we get cancellations. A times r to the n minus 1 minus a times r to the n minus 1. Those cancel. So there are only two terms that survive. So we have the term a from the top equation, and we're subtracting this term from the bottom equation. Hey, now what? Remember what the goal is? The goal is to find a formula for s sub n. So in other words, solve this equation for s sub n. On the left-hand side, we can factor s sub n out. We can write it as s sub n times 1 minus r. On the right-hand side, we can factor a out, and we can write it as a times the quantity 1 minus r to the n. And it's a good thing we said r does not equal 1, because now we're going to divide both sides by 1 minus r. We wouldn't be able to divide if r is 1, because we would be dividing by 0. But since r does not equal 1, we divide both sides by 1 minus r, and we get s sub n is equal to a times 1 minus r to the n over 1 minus r. So r does not equal 1, just to reiterate. And that's a pretty nice formula for s sub n. Remember, this is coming from a geometric sequence. So if the number r is between -1 and +1, then what do you know about the limit of r to the n as n approaches infinity? So we've seen this before this semester. You've probably encountered it before Calc 2. Well, the limit is 0. If r is between -1 and 1, and if the exponent n goes to infinity, the number goes to 0. Okay, so remember, if S sub n is, the sequence S sub n is the sequence of partial sums, from the sequence A sub n, and if the limit of the sequence of partial sums is equal to a finite number s, then what does that tell us about the infinite series of the A sub n sequence? It's also equal to S, right? Okay, so if -1 is less than r, which is less than 1, then the limit as n approaches infinity of S sub n, where S sub n is equal to a times the quantity 1 minus r to the n divided by 1 minus r. What does that limit equal if r is between -1 and 1? Well, the only thing affected by n is r to the n, and if r is between -1 and 1, r to the n goes to 0, and so the limit is a over 1 minus r, which is a finite number if a is a non-zero number and r is between -1 and 1. Okay, so what we can say is the infinite series of a times r to the n minus 1 is equal to a divided by 1 minus r when the value of r is between -1 and +1. Okay, so this is stated on the next page. Oh, this is what we were talking about. The geometric series where the terms are a times r to the n minus 1 as n ranges from 1 to infinity. So that just means a plus a times r plus a times r to the second plus dot, dot, dot. It's convergent if r is strictly between -1 and 1, and its sum is a divided by 1 minus r. If the common ratio r is less than or equal to -1, or if it's greater than or equal to +1, then the geometric series is divergent. Okay, let's look at an example. So I'm giving away some of the information. We have, in the next two examples, we have two geometric series. Determine if they converge or diverge. And if they converge, find what they converge to. Okay, the inside information is that this is a geometric series. How do we find the common ratio? Well, on a previous page, the formula for finding the common ratio is divide the n plus first term from the sequence by the nth term from the sequence. So we have infinitely many options. We only have 4 terms that show, but we could write -4 divided by 3. That's the common ratio, or -4/3. We could also use the third and fourth terms. We could divide -64/9. We could divide that by the previous term, 16/3. And when you do the arithmetic, you still get -4/3 for the common ratio. Okay, let's write this using the sigma notation, n starting at 1 and going to infinity. So this is the terms. We can write the terms if we write down the first term 3 multiplied by the common ratio, -4/3, and make the exponent n minus 1. And you can verify that this is the correct formula just by picking a few values for n and showing that you get the series above. You want to do that, or is it pretty plain? So I'll just do a couple of terms. When n is 1, the exponent is 1 minus 1, or 0. -4/3 to the 0 is 1, and so 3 times 1 is 3. And then when n is 2, the exponent 2 minus 1 is 1. 3 times -4/3 to the first is -12/3, or -4. See how that works? Okay, so does this infinite series, this infinite geometric series, does it converge or diverge? Does it diverge? What's that?
Diverge.
Yeah, diverges. How do we know?
It goes back and forth between the values.
Yeah, we know that it diverges because -4/3 is less than -1. So this geometric series diverges because the common ratio -4/3 is less than -1. So that's more words than is necessary, but that's all right, I guess. Okay, let's look at the next geometric series. So inside information, this is a geometric series. What's the common ratio on this one? What's the common ratio? So I guess everybody online's on vacation or something. There we go. So I got a correct answer online. Anybody in class?
3/4.
Yeah, 3/4. So divide the second term by the first, so we get 3/4. Just for practice, let's write down this geometric series in sigma notation. So n starts from 1 and goes to infinity. Okay, so if it's a geometric series, it's pretty easy to learn how to write what the terms look like. The first term is 4. Then we multiply that by the common ratio, 3/4 raised to the n minus 1. Okay, then we can use the formula for the sum of this convergent. This is converging because r is between -1 and 1. Okay, so this is going to add up to, or the sum is 4, that's the first term, divided by 1 minus the common ratio. So 1 minus 3/4 in the denominator. So we get 4 divided by 1/4, or 16. All right, let's move on to the next page. Okay, now we encounter the famous harmonic series. It looks harmless enough. The terms are 1 over n as n ranges from 1 to infinity. So that just means 1 plus 1/2 plus 1/3 plus 1/4 and so on. This is not a geometric series. So what do you think? Do you think this harmonic series converges or diverges? If you guess, you have a 50% chance of guessing correctly.
It's a diverge.
You say it diverges? Well, you're correct. It diverges. So even though we're successively adding smaller and smaller numbers, it still diverges to infinity. So we'll do a little computation here. So I'm going to pick certain terms from the sequence of partial sums. So S sub 2 is the sum of the first two terms, 1 plus 1/2. And we'll just note that this is 1 plus 1 times 1/2. Okay, the next term from the sequence of partial sums that I'm going to pick is S sub 4. So here we add the first four terms, 1 plus 1/2 plus 1/3 plus 1/4. Okay, but we'll note that this is greater than 1 plus 1/2. I'm going to replace 1/3 with 1/4 and keep that 1/4. Right, 1/4 is a smaller number than 1/3, so S sub 4 is greater than 1 plus 1/2 plus 1/2. 1/4 plus 1/4 is 1/2. So just note that this is 1 plus 2 times 1/2. The next term from the sequence of partial sums that I'm going to pick is S sub 8. So can you decipher what I'm doing or why I'm picking certain numbers from the sequence of partial sums? Okay, so let's go ahead and write out the terms for S sub 8. It's the sum of the first 8 terms, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. So this time, okay, this is greater than 1 plus 1/2. And then I'm going to replace 1/3 plus 1/4 by what I did above, 1/4 plus 1/4, which adds up to 1/2. And then for the next four terms, instead of 1/5 plus 1/6 plus 1/7 plus 1/8, I'm going to replace those with 1/8 plus 1/8 plus 1/8 plus 1/8. But 1/8 plus 1/8 plus 1/8 plus 1/8 is 1/2 again. So this is 1 plus 3 times 1/2. Okay, does anybody see the pattern? For subscripts from the sequence of partial sums, I'm picking powers of 2. So the first one, 2 to the first, 4 is 2 to the second, 8 is 2 to the third. So I know that it would be exceedingly tedious if I did another line. So I'll just sort of cut to the chase. The next one, the next power of 2 after 8 is 16. 16 is 2 to the 4th, so S of 2 to the 4th. And that's going to be greater than 1 plus 4 times 1/2. If we went through the same sort of process as we did previously, we would find that this partial sum is greater than 1 plus 4 to the 1/2. So what if I chose 2 to the power n from the sequence of partial sums? We would find that this is greater than what? 1 plus n times 1/2. Okay, well, remember the sequence of partial sums, these are coming from the harmonic series. So the limit as n approaches infinity of s sub 2 to the n, that has to be greater than the limit as n approaches infinity of 1 plus n times 1/2. But we know enough to know that the limit of 1 plus n times 1/2 as n goes to infinity is infinity, right? So this shows by comparison that the harmonic series is divergent. So we conclude that the harmonic series diverges. Okay, let's move on to Theorem 6. So this theorem is going to be useful to us in a roundabout sort of way. Well, not really roundabout, but anyway, if the series of a sub n terms as n goes, the sum of a sub n as n goes from 1 to infinity, if this series is convergent, then the limit of the sequence a sub n is equal to 0. All right, so we're given that the infinite series converges, and so if S sub n is the sequence of partial sums, if S sub n is the sum of the first n terms from the sequence, then that sequence converges. So it's equal to a finite number S, let's say. Okay, note that the limit of n plus 1 as n approaches infinity is infinity. Ergo, the limit as n approaches infinity of s sub n plus 1 is also equal to s. Okay, so s sub n plus 1 minus s sub n, what's that equal to? So s sub n plus 1 is the sum of the first n plus 1 terms from the sequence a sub n. And we're subtracting s sub n. That means we're subtracting the first n terms from the sequence a sub n. So what am I left with? So s sub n plus 1 is a sub 1 plus a sub 2 plus dot 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 plus a sub n plus a sub n plus 1. And we're subtracting s sub n, which is a sub 1 plus a sub 2 plus dot 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 plus a sub n. So what do we get when we subtract s sub n from s sub n plus 1? A sub n plus 1, that's all that's left, right? Then we can say the limit as n approaches infinity of a sub n plus 1, that's equal to the limit as n approaches infinity of s sub n plus 1 minus s sub n. Now what? Remember properties of limits that we went over those yesterday, I guess, or Wednesday? So we have two limits that exist, the limit of s sub n equals s, and the limit of s sub n plus 1 equals s. So the limit of the difference of the two sequences is equal to the difference of the limits. So this is equal to the limit as n approaches infinity of the s sub n plus 1 sequence minus the limit as n approaches infinity of the s sub n sequence. But the limit of each of those is s, so I get s minus s, which is 0. So to reiterate what this theorem is about, if the infinite series is convergent, then the limit of the a sub n sequence is equal to 0. Okay, we have less than 2 minutes left. So here's something that's important about Theorem 6. The converse to Theorem 6 is not true in general. So if you have an infinite series, and if it turns out that the limit of the a sub n sequence is equal to 0, the corresponding infinite series may or may not converge. Okay, we've already seen an example using the harmonic series. So we know that the harmonic series diverges even though the limit as n approaches infinity of 1 over n is 0. So make sure that you don't make that mistake. Just because the sequence of the a sub n terms goes to 0 doesn't mean that the series is convergent. Okay, we're out of time for today. We'll do the rest of this on Monday. So go ahead and sign in for attendance.